So in this recording, we're going to see a basketball shot up in the air. We're going to scroll through it. When Ryan gets to this point, we're going to take a look. Remember, it's not a projectile until it is in contact with nothing but the force of gravity. So right now it's still being forced up by Ryan's hand. As soon as he lets go of it, right about there, now the basketball is considered a projectile. Now we can consider that force diagram of just FG pointed down. So that is what you need to keep in mind for all these examples, is that once it has left the launch or the push or the shot in any form, the only thing that's acting on the ball is gravity. That's what a projectile is. And so that's going to be the guiding piece of information in your kinematic equations, that gravity is the only thing causing it to change its motion, and that acceleration to gravity is negative 10 meters per second squared in the y direction. So as we use that, we can kind of scroll through, and we see that this ball makes a parabolic arc. So we'll get it back to returning to its original height from right here. So if we go back to when Ryan lets go of it, we'll see some symmetry. The time it takes for the ball to get right about there to its maximum height is going to be the exact same amount of time that it takes to get back to its original height of where he let it go. We notice a couple other things too. My point about gravity, we notice that it's going up in the y dimension, and then it starts to, after it reaches that maximum height, it returns back in a downward motion. Once it's lost all of its upward velocity from Ryan's shot, it starts to drop back to the earth due to gravity. The really important thing to remember is that all of its motion in the horizontal is constant. There's nothing in the x dimension causing it to speed up or slow down. So whatever force Ryan put on it when he shot it, whatever push he gave it in the horizontal, is going to be exactly how fast that ball moves all the way until it hits the ground. So let's just take a look at some of the math in that basketball shot. So let's make sure we draw our x and y axes. Remember, x is our horizontal, y is our vertical. We'll put a negative y. It's extremely important to remember your signs in two-dimensional motion, because anything that's pointed in the negative needs to have a negative sign. Anything that's pointed in the positive needs to have a positive sign, or it'll get really mixed up. So if we consider the origin the point where all other forces are no longer acting with the projectile, it's just in projectile motion, it's going to follow a parabolic path. And a parabolic path has symmetry. It has symmetry about the vertex, or in this case, this represents the maximum height. That's where the max height is. That max height would be graphed right here on the x-axis. That's the max height there. So we also know that the time it takes, let's say this is time equals 0. That's the 0 time. This would be time half, or time at max height. They're the same thing. Half the time at the max height, and this here would be where the time total is found. So the time it takes to get the whole thing, if you want the time at the max height, you just use half of the total time. So that's going to be really important for figuring out some of the kinematic equations, knowing that time half is the max height. The only force that is acting on a projectile is the force due to gravity. And this force due to gravity causes all masses to accelerate at negative 10 meters per second squared, meaning that the velocity in the y dimension will be constantly changing by negative 10 meters per second every single second. So a quick example is if it is shot up into the air at 10 meters per second, it will be at 0 meters per second after 1 second. That's a lot of complicated language. But that's just saying that it's going to lose 10 meters per second every single second. So at the top of that 10 meter per second launch, it should be at 0. Another really important thing to remember is that there are no forces acting on this object in the x dimension. No x forces. So what we learned in our last unit is if there are no forces, in other words, it's the same exact thing as a balance, there's no net force on an object, there will be no acceleration. So there's another proof that there will be no acceleration in the x dimension. It's all the acceleration will be happening in the vertical y. So we can totally ignore the x dimension in terms of acceleration. Now that we looked at the path of a projectile and we know the forces that are acting on a projectile, let's look at some of the equations that we would use for two-dimensional projectile motion. So in the y dimension, we know vertical, we ask ourselves acceleration, question mark, let's put a little box. Absolutely there's acceleration. And what is it? Negative 10 meters per second squared. In the x dimension, which is the horizontal, we ask ourselves, is there acceleration going on? Question mark. And there is not. No acceleration. So you put a big no. So we know that all of our equations in the x dimension are going to be constant motion equations. So let's take a look at a couple of those equations down here. We know that there are some very basic equations with constant motion. And they're all rooted in this idea that we learned from our buggy lab way back in the beginning of the year. We figured out that the change in the position is just equal to the velocity times the time. So how far is something gone? Well, it's just how fast it's going multiplied by how long it's been going that fast. So that's going to be one equation. If we do a little bit of rearrangement, we can say that the velocity is just the change in position over the time as well. X dimension couldn't get any more easy. It's just going to be one-dimensional motion. If you know how fast it was going at the start, it's going to go that fast the entire time. So you can figure out how far something moves down a field or how far something moves away from the initial launch just by using how long it's in the air and the velocity that it was shot with. In the x dimension, though, the fact that there's this acceleration complicates things. We need to use accelerated motion equations. So one accelerated motion equation we know is that the change in velocity is equal to the acceleration times the time, meaning that how much is the velocity going to change? Well, if we know the acceleration, which we do, this will always be the acceleration, and we multiply it by how long it's been accelerating or how long it's in the air, we can figure out how much the velocity has changed. This equation is going to be really useful when we have to figure out if something's launched up at an initial velocity, how long is it going to take to get to the max height? Well, we know that velocity at max height equals 0 in y dimension. We'll just say yd. In the y dimension. So that's a really important fact that we use. If we want to know about how far it's gone or what it is, its max height is, we're going to use the delta y equation, which would say the velocity initial in the y times the time plus 1/2 the acceleration in the y times t squared. Now you just have to be careful what time you're using. If you're trying to find the max height, you would use t half or t max height. Remember, acceleration in the y is always just negative 10 meters per second squared. And your initial velocity in the y is whatever it's launched at, the y component. So if it's launched at an angle, you need to find just the y component in order to understand this type of motion. And finally, as I just mentioned, if you have an initial velocity at some angle here, so this is our x and this is our y, then we need to use a little bit of trigonometry to figure out. It's not helpful to understand a vector that's in the x and the y dimension. So we consider this to be the initial in the x, and we consider this to be the initial in the y. And let's just say this is angle theta. Okay, well, Vix just equals the hypotenuse, which is the initial velocity, times, it's the adjacent side, so it'll be, we'll use parentheses here, times the cosine of theta. And this will just equal Vi times the sine of theta. And once you get that, you'll have the component of this initial velocity that points directly along either of the dimensions.